Good afternoon, and welcome to the second How TrueAllele Works. Today we'll be talking about degraded DNA and allele dropout. Let's begin with degraded DNA. This is a case where a man in Pennsylvania, in Reading, was accused of killing a woman in a parking lot of a hospital and stabbing her 30 times until she bled out. The key evidence in Commonwealth versus Lyons was a DNA mixture, the neck area of a sweatshirt. Now, this sweatshirt had been found after police cadets had combed a garbage dump for several days, and they found this discarded sweatshirt. And in the back neck area of the sweatshirt, as you can see, with a blue arrow, was a DNA mixture that contained largely the victim and also some other individual. So let's talk about degraded DNA, because that's what was found here, and see what the issues are with degraded DNA. Ordinarily, when you have a DNA fragment, as shown on the top, and it's copied with polymerase chain reaction, or PCR. If the DNA is intact, then the enzyme can read from one end of the strand of DNA through to the other strand, and that will make a copy. So in order to copy a fragment of DNA with PCR, whether it's 100 base pairs, 300 base pairs, 500 base pairs, the DNA has to be intact, and there can be no breaks in the DNA. What happens with degraded DNA is that breaks appear. Degradation can occur when enzymes from bacteria cut the DNA, and now between the two ends of that fragment there is a break. Degraded DNA breaks can be introduced by ionizing radiation, by extreme heat, but it's often bacteria that grow in warm or moist conditions over a long period of time, and their enzymes will chop the DNA. Once there's at least one break in the DNA fragment, then the polymerase enzyme can't copy through that broken DNA. And so even though that DNA is present in the sample, and it's present in the test tube of the extracted DNA, it's invisible to the STR, short tandem repeat process, because the copying can't occur. Now, longer molecules are copied even less. And the reason is that only one break is needed to stop the copying process. So with a very short fragment, like we see on the top left, the odds of a break may be less. And once the fragment becomes a little bit longer, like we see in the middle, there's a greater chance of having at least one break. And once the fragment becomes longer and longer, then the chance of 2 or 3 or more breaks increases, and so there's a chance of at least one break. And then again, that fragment will become invisible to the PCR readout process. So let's take a look at the density of breaks and the probability that a copying event actually occurs. So the break density is the probability that there's a break at one letter in the DNA chain, at one nucleotide. For example, if the chance is that every 100 letters there'll be a break, then p, little p, is the probability, 1 in 100, that there's a break at a nucleotide. So we can think of that as the density of breaks. Is it every 100, every 1,000? Q is 1 minus p. That's the probability that no break occurs at a nucleotide. Now, in order to get a copying event to occur, there can be no breaks. And each of these events that there's no break at a DNA letter, at a nucleotide, are independent events from the first, second, third, fourth, up to the length n, maybe 200 or 300, of the entire sequence. So the value of Q to the N is the probability that no break is seen across the entire fragment in N nucleotides. And that's the copy probability. What's the chance that we can copy through this fragment? So you see it depends on the break density, P, because Q is 1 minus P. It also depends on N, the length of the DNA fragment. Now in science, we often take a look at decay curves. And here, the decay factor lambda, that's the Greek letter L, little l, lambda, is easily related to the probability that there's a break, because just by some algebra, Q is equal to e to the natural log of Q, and then if we set lambda equal to the negative natural log of Q, that guarantees that lambda is a positive number. Since the log of a number between 0 and 1, that's a probability, will end up being negative. So that is the decay factor, e to the minus lambda. And if we want to see how breaks occur, what we really want to understand is how this break density P translates into the copy probability. So the copy probability is Q to the N, which is the same as the decay function, e to the minus lambda n. And let's take a look through this table and see what happens. In the first row, when P, the break density, is 0, then Q is 0, and lambda becomes 0 when you plug that into the exponential. And we see that the copying probability, at least with regard to degradation, is 1 whether the number of letters in the DNA is 100, 200, or 400. And the half length, that is the length of DNA at which half of the signal is gone, in this case is infinite. In other words, when there are no breaks, then you get the full copy. But what happens in the next row when P is 0.001? That is, there's a 1 in 1,000 chance of a break, and that's the break density. Well, we see lambda is the same after the math is done. It's also 0.001. In fact, you'll notice that for small values of P, lambda, the decay factor, is essentially the same as P, the break density. That would change if P was a lot higher, but then all the DNA would be gone. It wouldn't make much of a difference. So let's notice that the decay factor, lambda, is essentially the same thing as P, the break density. So when the decay factor is 1 in 1,000, 0.001, then we see in gray that as the DNA length increases from n equals 100 to 200 to 400, that the copying probability reduces from 0.904 to 0.189 and to 0.670 respectively. And at that level of 1 in 1,000, the half length is 693 base pairs. So that's the point at which half the DNA is gone. In the third row, with a 2 in 1,000 break density, lambda, the decay factor, is the same as P, 2 in 1,000. And the copying probability now starts getting lower, from 0.18 with 100 base pairs, 0.670 with 200, down to less than a half, 0.45 at 400 base pair. And at this point, the half length is 346. And continuing in this way with 5 in 1,000, we see there's even less of a copying probability. It'll drop from 0.606 at 100 base pair down to only 13.5% at 400 base pair. And at if the break density is 1 in 100, the DNA really starts disappearing. The copying probability, even for a short fragment of 100 base pair, is 0.366. And by the time you're out to 400 base pairs, it's down to about 1%. And now the half length is 69. Let's look at this visually and take a look at these, what these DNA curves look like. First, let's look at this, the axes here. On the x-axis, we're looking at, in 100 of base pairs, the length or the DNA size of a fragment, and the y-axis is showing an amount of observed DNA on an arbitrary scale that's up at 80 and then decreasing. With degradation, a longer DNA molecule will make fewer DNA copies, and the probability of copying, or the signal decay, is the standard decay formula e to the minus lambda n, where lambda is the decay factor and n is the length of the fragment. Here in this curve, lambda, shown on the right, which is the same as the break density, is 3.5 breaks per thousand, 0.0035, and the half length is 200 base pair. Now, looking at our curve, we can see the effect of the half length. If the top of the scale is 80, halfway down is 40, and following the solid blue arrow, that brings us to 200 base pair. If we have it again to 20 on the scale, then that brings us out to plus another 200 base pair, or 400 base pair. If we have the amount again to 10 on this relative scale on the y-axis, that brings us out to another 200 base pair, or 600 base pair. So this is what a decay curve looks like. For a fixed amount of additional half-length, we have the amount of observed DNA. And so as the fragments get larger, the amount of signal gets less. This reduces match information in a general way by this succession of events. If we have degraded DNA, then that will produce lower peak heights. The lower peak heights will provide greater data variation in the peaks. And if there's more relative variation, that will produce more genotype uncertainty. That uncertainty diffuses genotype probability away from the true contributors to other possibilities that aren't the true contributor, and that has the effect of reducing DNA match information. Now, of most important interest in interpreting DNA evidence is differential mixture degradation. That is, each contributor may have a different amount of decay. Its factor can be different based on the contributor and how broken down or degraded each contributor is. So in this picture, what we see is a 4-contributor mixture where the TrueAllele computer has separated the decay curves. The least decay is shown on top in a cyan color, and the most decay is shown with a bottom decay curve in brown. And these different amounts of decay will change the apparent peaks and their heights based not only on mixture weight, but also on the amount of decay. So let's see how that works. Looking at the same picture, imagine that we're just looking at 2 of the contributors to make it simpler, the blue on top and the brown on the bottom, and we're looking at a pattern of, say, 4 alleles at a low molecular weight locus towards the left of this picture, closer to 100 base pair. Before degradation really kicks in, it may be that the brown contributor has more DNA than the light blue or cyan contributor, and that's shown in the pattern on the top left. But as we move from left to right and we get more out to 400 base pair, the increased degradation of the brown contributor may flip that pattern, and now even though there really is more of the brown contributor present in the tube, because of the cuts in the DNA fragment, it can't be read. And so we're not seeing it in the peaks. And that's why it would appear that when we take the data measurement, the peaks from the blue contributor look higher now than the peaks from the degraded component in brown. And we get a flipping where towards the left, the brown contributor might appear to have twice the peak heights of blue, but towards the right, blue may have twice the peak height of brown. And so this affects the mixture weight, and which is varying as you go from left to right across the degraded loci. And since mixture weight is an important part of inferring genotypes and separating them out, it can affect the genotype inference as well. So this is the data in our case, and this is what degraded mixture separation looks like for this 2-contributor mixture. On the top, I'm showing how TrueAllele's thinking about it. It's just Bayes' theorem. The posterior probability is proportional to the likelihood times the prior. That's all it's doing. So the distribution of the decay parameter lambda at different values given the STR data is proportional to the likelihood, how well that parameter explains the data, times the prior probability of the parameter lambda. And in this case, the way TrueAllele separated the DNA is that the victim's DNA, shown in gray on top, was not terribly degraded, and there's a parameter lambda 1 that the computer inferred as a probability distribution. And the blue curve shown on the bottom showed a much sharper decay, and this was the other DNA that was present that was not the victim, and its decay factor was much greater. And the computer was able to separate out these decay curves and estimate lambda 1 and lambda 2. That resulted in a mixture weight separation. The reasoning is again Bayes' theorem, with a posterior distribution of mixture weight conditioned on the data is proportional to the likelihood. How well the mixture weight along with the decay factor explains the data, probably the data given these variables, times the prior of mixture weight. And here we see the mixture weight separation is giving a major component, which was the victim, shown as a gray bell curve, with a mean around 70%, and the mixture weight of the second component is shown in blue on the left with a mean of around 30%. So the computer, when it accounts for degraded DNA, is finding a 30-70 mixture. Now, if you run the computer and you turn off the degraded option and you don't have that in the model, what the computer will find, because of the large amount of degraded DNA and the flipping of the ratios of peaks, is that would be a 15 to 85. So the computer can get a more accurate estimate by considering the degradation when it computes mixture weight. The result in the genotype separation is that, looking at the second contributor, the posterior distribution, the probability distribution of over the allele pairs for each locus of the unknown contributor, given the data, is proportional to the likelihood, which is how well the data is explained by lambda, the decay factor, W, the mixture weight, as well as the genotypes that are used and other variables like stutter and so on, times the prior probability of the genotype. This is just Bayes' theorem again. The posterior probability given the data is based on how well parameters explain the data as a likelihood times prior. The picture that we're seeing is showing the genotype separation. So for each of the loci listed here from PowerPlex 16, let's take a look at the second row, CSF, as a locus. There were about 100 possible allele pairs before the computation started, and then what the data's done is it's concentrated probability into about 5 allele pairs to extract information, with most of the probability concentrated on that first allele pair, the 8-10, as indicated by the tall blue bar. So here the blue bars are showing the posterior probability, the inferred genotype probability of each contributor. The green bar is showing, in the middle, is showing the suspect's genotype when a comparison was made, and the brown bar, which is very low on the right, is the population probability. So what we see is that at most of the loci here, the computer has correctly concentrated the probability of this degraded 30% contributor, as shown by the blue probability distribution, next to when a comparison was made after that objective determination, next to the genotype shown in green of the suspect. Now, when that objective genotype was formed, different methods were used. The human review method that was used initially was the CPI method, combined probability of inclusion, and that produced a match statistic of 42,000. In the middle, the match result when TrueAllele did not solve for degradation and didn't consider that as a parameter was that a match between the suspect and the evidence was 1 billion times more probable than coincidence. And when the computer did solve for degradation, and it considered that factor of decay, it then found that a match between the suspect and the evidence was 1 trillion times more probable than coincidence. So let's take a closer look at what TrueAllele did between its considering degradation and not considering degradation. So what we see here is the likelihood ratio of the comparison of an inferred evidence genotype relative to the suspect for a population, and it's locus by locus, amyloid, CSF, D13, D16, all the way down through VWA, alphabetically. We're seeing two different likelihood ratios expressed as the log of the likelihood ratio in additive band units. And what we notice is that the one in darker blue, when degraded DNA was not considered, tends to be a smaller number and a little more to the left than the second log likelihood ratio that was inferred considering degraded DNA, and that light blue number is a little bit more to the right. In fact, they're almost the same, except at locus D3, where degraded DNA did a better accounting for degraded DNA, did a better job of looking at a stutter peak. And in fact, even though overall, looking on the right, there was a difference between 1 billion, which is a 1 followed by 9 zeros or 9 band, and then considering the decay factor, 12 band or 1 trillion, a 1 followed by 12 zeros. Overall, the improvement wasn't that dramatic, except at that one D3 locus. And in fact, that's what we see. Considering degraded DNA in TrueAllele will typically give an improvement of maybe a band or 1 band, but it's not dramatic. You typically don't get a difference of 6 band or a factor of 1 million. And the reason for that is that the mixture weight modeling in TrueAllele is already hierarchical. So what that means is, if you look at the hierarchy diagram, the template weight shown in the third row is what's affected as an average by the decay factor. And the locus weights shown in the second row are being computed as separate parameters for each contributor for each experimental data locus, shown in green in the top row. And since these customized mixture weights at each experimental locus are already very close to the data in TrueAllele's hierarchy, as part of the 100 variables that it's looking at when it's solving an STR mixture problem, the template weight and the effect of degraded DNA isn't as great as it would be if it were a non-hierarchical model. So just by having hierarchical mixture modeling, the computer's largely getting it right, and accounting for decay factors is just additional icing on the cake. So in this case, TrueAllele was helpful in securing a conviction of Glenn Lyons. He received the death penalty for the murder of Kathy Liebeck. Moving on to the second topic, let's take a look at allele dropout. So here's some data at a high molecular weight up in the 400s of DNA length, as seen by the axis in the electropherogram horizontally, with very low RFU values shown on the vertical y-axis. We see two peaks, a 12 and a 13, but from other information, we know that the genotype, one of the genotypes that contributed to this mixture was a 713 at this locus. So allele dropout is a phenomena when an allele is present in a contributor genotype, here 7 and 13, but it's not seen as a peak in the STR data. So here the 13 is visible, but the 7 is not visible. How does TrueAllele solve for allele dropout? Well, the same way it solves all of its problems. It does it by genotype modeling. It compares two patterns. It compares the pattern of the fixed data shown in the green peaks in the background in this electropherogram figure, and it compares it against tens or hundreds of thousands of possible genotype explanations where different amounts of allele pairs are added together, and then other factors like stutter and peak variation and relative amplification are accounted for. And then the patterns that are formed from the genotype hypotheses, in this case of 3 different genotypes, and their allele pairs, are compared against that fixed data, and the proposed explanations keep changing, the data doesn't, and explanations that better explain the data in a probability function receive higher likelihood. So let's see how that helps explain 3 different types of data. First, we have faithful data. This is data where, as you see in the electropherogram, there are good, strong, balanced peaks for a 20 and a 22 as alleles, and we know from other information that a 20 and a 22 actually did contribute to this mixture. The computer doesn't know it when it solves the problem, but we do. And in this situation, let's take a look at the genotype and the likelihood ratio. So this is one of the views that we look at when we go through and review DNA evidence for reporting purposes. In the bottom left is the same data window that we just looked at, showing 2 tall peaks at 22 and 20 and a lower peak at 24. The top window is showing genotypes, and the bottom right window is showing the likelihood ratio. Let's take a look at the genotypes. In blue, the blue bars are showing that most of the probability inferred when the computer separated out the mixture data without knowing who any of the contributors were. The computer placed about 60% of its probability on 2022 as an allele pair at the FGA locus, with other events still being possible as shown by other blue bars. In the comparison that gets made afterwards, now we can see that the comparison reference genotype does have a 2022 allele pair. And if we look at where that green bar is to make the likelihood ratio calculation, the ratio of the blue bar at 2022 on the top left to the brown bar, which is the population random probability, is around 20. And on the bottom right, we see that calculation, that ratio is 22, and that's the likelihood ratio. And shown is a blue bar to the right with the log of the likelihood ratio at this FGA locus in band units as a 1.3456. So this is the picture of DNA when at a locus, when it's the pattern that we see in the data is faithful to the allele proportions that are present in the sample. Let's look at a second case of imbalanced data, imbalanced peaks or alleles. Here, in this 3-person mixture, we know from other information, though again the computer doesn't when it solves the problem, that there's a 10 and a 12 as an allele pair that's contributed as DNA, but the peaks 10 and 12 are imbalanced. Now, looking at the same 3-window view, we see the data on the bottom left, and now the genotype is showing not tremendous concentration on just a few possibilities, but a diffusion across maybe 20 possibilities shown in the blue bars of the inferred genotype. And when you compare that with the brown population genotype, we see that it's very similar at many of these allele pairs, maybe a little bit bigger at the 10-12 possibility that in green corresponds to the genotype of the actual contributor, since that blue bar of evidence probability from the separated contributor is a little bit larger than the brown bar. That ratio is bigger than 1. In fact, it's about 1.5. And on the bottom right, we see a little bit of weight of evidence, it's greater than 0, 0.1895, expressing that 1.5 likelihood ratio for the imbalanced data. Now let's take a look at allele dropout data. Here we have from other information that a 7 and a 13 contributed to the genotype at this to the sample at this locus as one of the contributing genotypes. But the 7 allele is not present in the data. It's completely missing. The 13's there, but the 7 isn't. What does TrueAllele do in this situation? Looking at this 3-window view again, and the bottom left, there's the same data we were looking at. Now, on the top genotype view, we see that TrueAllele has put probability based on where the data said probability should be for one of the contributors to the mixture. It's a 12, 13 data peaks at low levels, 60 and 80, and so most of the probability, as we see in the top middle, was placed at the 12, 13 allele pair. A 12, 12 is possible, so that gets about 25% probability shown on the top left. And a 13, 13 is also possible. And so we see a taller blue bar at around 15% there as well. So that pattern of where the taller blue bars are corresponds to how probable these allele pair possibilities are based on the data that the computer sees. Now, in fact, there was dropout, and the 713 of the actual contributor gets some probability. Every possibility gets some probability, but not that much. And in fact, if you look where the green bar is in the top, the blue is maybe of the third of the height of the random probability of brown, just looking at where that green bar is of the known 713 genotype. Since blue has 1/3 the height, the evidence genotype, relative to the population, shown in brown, we see on the bottom right, in red, the 0.35 is expressing that 1/3 probability, and in log units, this would contribute a negative weight of evidence, an exclusionary amount of negative 0.4535, showing that the data is not supporting the inclusion of a 713 individual at this penta locus. So we've done studies on dropout and imbalance. This is from a talk that I gave at the AAFS meeting in Washington a year and a half ago. This is collaborative work with the Allegheny County Crime Lab here in Pittsburgh. So this is a part of that study where there was no CPI score recorded. There was no human review at this locus or any of these loci, but there was a TrueAllele result. And so what we're doing in these histograms is taking a look at what happened at each of these loci where there was a TrueAllele result but no CPI result. The x-axis is showing the amount of information as in log LR or band units. 0 means a log LR of 1, an LR of 1. A 1 means a number of 10. A log LR of 2 all the way on the right is a likelihood ratio of 100. And moving to the left, a -1 is a LR of 1/10, and a -2 is a statistic of 1 in 100. The blue histogram is showing the distribution of match statistics at a locus when the locus is free of dropout and imbalance. And this is the evidence that's not being used by human review. TrueAllele is getting about the same amount of information, about 2/3 of a log unit, as it does for information that people do use. But of most interest is the red distribution, where there is dropout or imbalance. And here we see that the red bars are between -2 and 0. And this is the distribution with an average of -3/4 of a log unit that shows that when there is dropout or severe peak imbalance, then TrueAllele will assign a negative weight of evidence, a log LR that's less than 0, indicating support for exclusion. Now, this is the computer, of course, adds up the results at all the loci, so if only a few loci have severe dropout, the overall effect is still an inclusion. This data is from a study that was presented at the International Conference on Forensic Inference and Statistics in Holland this August by Atte Kloosterman from the Netherlands Forensic Institute, and it looked at different software programs using different methods for complex DNA mixture interpretation. What we're seeing here is the results with TrueAllele. On the x-axis, we have different amounts of DNA and different numbers of dropouts. 1 nanogram with 2 dropout events, half a nanogram with 8 dropout events, a quarter of a nanogram with 14 dropout events. And on the y-axis, we see the log of the likelihood ratio, the amount of information. And we see that as the number of dropouts increase and the amount of DNA decreases, the match statistic goes from about 13 or 10 trillion down to 9 or about a billion. And then finally, with a quarter of a nanogram on this two-person mixture, looking at the 10% minor component, to about 7 log units or 10 million. And this is consistent with studies that we and others have done on TrueAllele. Dr. Kloosterman also presented results from programs that have thresholds and drop parameters, including a star mix, LR mix, and lab retriever. And what we see is that all the way on the left with 1 nanogram and 2 dropout events, a more continuous method is preserving much of the information present at around a statistic of 1 trillion, and the dropout methods are giving results close to CPI with stats at around 6 zeros or 1 million. But as the number of dropouts increase and the quantity of DNA goes down in this 10% minor contributor, the information starts disappearing. And instead of preserving the information up at the 9 band level, it starts heading down towards 0. And this continues as we move over to a quarter of a nanogram with 14 dropouts, and the information again is essentially gone. And this is due in part to the idea that whereas genotype modeling may have 100 parameters to try to explain the patterns and objectively look at the results just from the data to infer a likelihood ratio. Methods that might oversimplify and only use maybe 2 parameters, like a threshold and a drop parameter, don't have enough dimensions to account for the complexity of the actual mixture data, even in a simple 2-person mixture. Okay, well, we'll start questions in a few minutes. We now have finished part 2 of how TrueAllele works. Part 1 on genotype modeling the likelihood ratio is posted on our webinar webpage, as will this webinar be in a few days. On December 18th, we'll continue with part 3, talking about kinship and paternity.